Now I'm wondering if Ms. Christy Walsh is here. Yes, I see a hand. Great. And also the team from Emprimus is going to be led by Dr. Frederick Faxvog. Now he's had basically a 40-year career of R&D and strategic planning in places like Honeywell and the physics department of General Motors. So what we're doing now in the shift at this moment is you've heard a lot about the FERC, or Federal Energy Regulatory Commission, proposed ruling that focuses industry attention on the problem of geomagnetic disturbance and what they'll do to create standards for that. And from the legal department of FERC right now, for a few minutes, we will hear a little bit about that and what your relationship might be to commenting on that, the significance of it, and so on, prior to the time we hear from industry. So at this time, I'd like to have Ms. Walsh come and maybe take a moment to describe her role, the office you're in, and the significance of this proposed ruling, and what you think we all ought to learn about it. Christy Walsh.
Thank you for having me. I feel a little bit outmanned here in front of all of you who really have done a deep dive on these issues. First, I must give the federal disclaimer. I don't speak on behalf of the commission or any individual commissioner. I also should say I don't speak on behalf of my technical staff. As he said, I am just a lowly lawyer. Energy, I should give you just a very short description of our authority in this area. Energy Policy Act of 2005 was enacted after that big blackout in 2003. It gives us authority over the reliability of the bulk power system. We have authority over an electric reliability organization, and that organization creates mandatory reliability standards that it gives to the commission that we approve and then become mandatory. We can also we have certified the North American Electric Reliability Corporation as that, what we call ERO. We can also direct NERC if we say there's something that isn't covered, and we can direct NERC to cover that. We started hearing from you guys, there's this GMD issue. Nobody's looking at it. Why isn't the federal government doing anything? And so we started looking at it. We did the Oak Ridge study with DOE, and NERC did 2 separate studies. And so finally in April of this year, we did a big technical conference. We invited NERC, we invited industry. Some of the people in this room were there and either spoke or were just in attendance. And we heard a lot of things. But one thing we heard was this is a problem. Some people said we don't know how much of a problem it is. We don't know when it's going to be a problem. We don't know how to fix it, but it's a problem. And then we started looking at the studies, the Oak Ridge study, the NERC reports, the EMP Commission reports, the NAS workshop reports. And we concluded that there's a gap in standards regarding GMDs. And so on October 18th of this year, the Commission issued what we call a Notice of Proposed Rulemaking, proposing to require NERC to create a standard that would cover what the Commission felt was to address this potentially severe, widespread impact of GMD events that others have spoken so much better than I could ever do today. And I think you sent out yesterday, so you all have that electronically, and I thank you for that. The draft notice of proposed rulemaking basically proposes that NERC develop the standard in 2 sections. We decided we need to get something done quickly. And so first, within, I believe, 90 days of a final rule on that matter, NERC would have to give us operational standards. What we found was a lot of the utilities don't even have anything on paper where somebody could say an EMP is coming and you need to do something. If your systems aren't hardened, you need to do something. You need to have studied and figured out exactly what you need to do to protect yourselves. So within 90 days of the final rule, NERC would have to give us standards, and the utilities would have to have a plan for operationally how they would deal with that message that would come from us or would come from NOAA or would come from NERC. The second step would be a longer-term issue. We would want NERC to develop a standard that would require the utilities to do initial and ongoing assessments of the impact of GMDs on the equipment of the system as a whole. Based on those assessments, the utilities would then have to figure out how to implement a plan so that basically uncontrolled separation, cascading failures, damage to critical or vulnerable system equipment, or otherwise wouldn't happen. And the reason this isn't specific, it doesn't say exactly what the utilities wouldn't have to do, is what we've heard from conferences, from the studies, is that every utility is different. Their transformers are different, their topology is different, they're at different latitudes. And so the studies will show exactly what they have to do. And they have to show that the study supports what their mitigation would be. And the standard they would have to give us in 6 months after a final rule. And we said we didn't set out exactly when the implementation of that standard would be, but we did say they had to support whatever the implementation would be. Now here's why I'm really here. People in this room don't interact with the Commission as much as some of our utilities do, but you guys have the valuable experience on these issues, and we really want to hear from you on this rule. You guys have the experience on these issues. You guys can tell us what we're not seeing, what we are seeing, what we're doing right, what we're doing wrong. You guys can, tell us the need for the rule. I heard some great thoughts on the cost, the need, whether with the specifications of the rule. And so we're asking that if you have thoughts, provide them to us in writing. Because of the vagaries of the Federal Register system, the comments are due on December 24th, so Merry Christmas to everybody. But that's what we're asking you to do, and I'd be happy to take any questions. I've created a document that has some comment procedures because I know most of you don't interact with the Commission very often. I have cards. I'd be happy to talk to anybody, and I'd be happy to answer any questions.
Okay, thank you very much. Are you going to be able to be here for a little while yet? Okay, so if what I'd like to do is save the questions at the end, so be thinking about them. Also, did you want to put some of these on the table back there? Right outside, yes. And don't go away because you'll have questions, I'm sure. And now I want to bring up our next guest, and we need to make certain that his slides are the way he would like to have them. And this might take just a moment, so we'll take a quick 1-minute pause.
That's back up, and this is back down, so it's this one and this one. Okay. So, what you're seeing there. Okay. I guess you can click on this too. That also does it. But I think it's easier if you do this back here. You don't have to mess with this. I think if you this is up and down. That's easier. Okay. Yeah. Okay. Okay. Is there a pointer? I think so. I think this is the pointer. Okay. Yes. But I'm not sure how to work it. Okay. Maybe it's the red button. There you go. It's that red button. Okay, I want to touch on what our company is doing. Emprimus is a company located in Minneapolis, Minnesota. Our goal is to invent and develop products
that are very effective and low cost to protect against EMP, intentional electromagnetic, and GMD threats. So today I'm just going to show you and bring you up to date on two of the products, one that we call solid ground. The others are inferential detector, inferential EMP detector. Now, both of these products are presently available in limited, and our company can produce in limited quantity. But our intention is that when the volumes go up, we're going to license these out to other companies that are capable of producing in large volume. But both are available today. The solid ground product that you see in the upper left, that's a unit, and right there it's shown at the Idaho National Labs, where we put it in the grid and tested it in a real live grid. We did this in September, and it was a one-week test funded by DOD and DITRA, the part of DOD. And so it's real. And that device, that system, is now available for $250,000 a piece to protect and do neutral blocking on a transformer. And in fact, in that location, we had it connected to two transformers. And what we found out is we can connect to 3 or 4 transformers with one unit. So the cost per transformer has suddenly come down to, say, $80,000 to $100,000 per transformer. So this was recently tested out there at Idaho. We now believe that we will be getting an order very shortly and be putting it into a power grid for ongoing testing and evaluation. The other product is our inferential detector over in the lower right. And this product is now up and running, been tested, and we already have an order for several to a large utility company, which we cannot name right now. But they have ordered a couple because they believe that they're getting pinged with intentional electromagnetic. And so they want to identify that and determine if that's the case. So, and that product is now about $16,000 per detector, and that comes with the display software and all the software you need to incorporate it into a security system. You can incorporate it in with your security cameras and so on. So you're really detecting the EMP threat or IMI threat. Well, let me try this. There we go. So the solid ground system, and in a minute I'll describe how it works, but its intent is to protect the power grid from solar storms and electromagnetic pulse. It's automated protection. The transformer is always grounded, effectively grounded. You'll see 3 paths to ground for the neutral, but and when called upon, it blocks the neutral. It's a neutral blocking device. Uses all commercial available parts. So there's nothing special in any part of this that we build. It's all off the shelf. So we just put a system together. It's been laboratory and field verified. It's factory assembled and arrives all installed. It can be put on simple piers, as shown in the diagram here at the bottom. And it offers some really good financial operating advantages. Okay, here's a brief, just a brief little sketch on how this works. The transformer neutral is connected through a series of switches, a switch assembly, and then through a milliohm shunt resistor. This shunt resistor is nothing more than a large chunk of brass. So it's not really a resistor, it's just a chunk of brass. That gives us a reading. It tells us when we're seeing and measuring GIC in the neutral. At that point, or if we detect harmonics on the line, either signal will trigger the switches to open. When the switches open, then we're grounding the system through a 1 ohm resistor and a 1 ohm impedance capacitor bank. Now this is very low impedance that we're putting in, so it will not cause any resetting of the relays in the system. And I should point out that we believe 99% of the time we will be grounding the transformer just like it's always grounded, through a metallic path to ground. When we detect, so we're here, what we're doing is we're sensing and then protecting. And so when we sense the presence of GIC or harmonics, we then ground it through the capacitor. Now in the very unlikely case that while we're in the protection mode, we have a ground fault, we have a surge arrestor. And so if we happen to have a ground fault while we're in the protective mode, the surge arrestor takes the first hit, goes into the so-called pressure relief mode. We detect that with that current, and we reclose the switches. So now we're just back in the unprotected mode, but we're still back in operation. So the transformer should always be grounded. So that's kind of a simple explanation of how this works. Let's go forward. There we go. Okay, first, we took this arrangement, this circuit arrangement, and we modeled it. We modeled it with the University of Manitoba that has a really, really good PSCAD simulation tool. And we found that even under various ground fault conditions, everything was going to work, and everything worked nicely. You wouldn't see resonances. The resonance die out real quick because of the resistor. And all of these, some of these issues that could pop up were dispelled at that point. We did ground fault testing in Philadelphia at the Kima Labs, and we took, I believe it was 15 surge arresters through the pressure relief mode, and everything worked as planned. The surge arresters, after they've gone through that mode, have a resistance of about 2 to 10, it varies from 2 to 10 ohms. So they're still conducting, even though they've gone into the pressure relief mode. So the testing the ground fault testing was very successful. And then out at Idaho National Labs in September, we tested in a live grid that was connected to the western grid. And this was 1 week of testing out there, and the system worked as expected. Of course, we did not have any ground faults there. We didn't expect any. But the switching occurred. You would hear the transformers, when GIC was injected, you would hear the transformers shaking and going through their thing. It was connected to 2 transformers in one test. And as soon as we detected the GIC, then there was a delay. We didn't want any false alarms. There was a bit of a delay to make sure it was GIC. And then we opened the switches, and then you can see the GIC is blocked. There's just a little overshoot here, and you're right back to zero current. So everything worked swell out there. The second test was hooking solid ground onto 1 transformer only and injecting current, trying to inject current into 2 transformers. Well, the second transformer allowed it to pass. And so we went up as far as we could go before they did not allow us to go further. We got up to 2% harmonic, and some guy down the line 13 miles away on the radio said, enough. That's as far as we're going. So, and that was expected. But it did work on the transformer it was protecting. Let's see now. Oh, we just talked about this, so I don't need to cover that. Now, the next thing I'm going to talk about, though, is to see what the effects are in a power grid. We've teamed with Power World and American Transmission Company out of Wisconsin. And what we've done is we've collected the data for the Wisconsin and Upper Peninsula grid, all of the connections in the transmission grid, the resistances, the configurations, grounding configurations, and all that data, and put it into the new Power World model, which includes GIC. So they can now calculate GIC and then see the effects on power flow with this new modeling tool. And Power World's not the only one. GE, Siemens, and we think Mitsubishi are all coming out with this kind of a tool. So I can't go into all the details here because of time, but I'll show you some of the results. Not. Here we go. Now this is the voltage plotted here on the lowest bus, and this is the voltage as a function of the geoelectric field that we're applying in the Wisconsin grid. A simulation, of course. The baseline, without any protection in place, is the blue line right here, and it comes down at about, the voltage collapses at about 21 volts for geoelectric field, volts per kilometer. Now, as we simulate the addition of neutral grounding in these transformers, we're doing it 5 at a time. So we pick the 5 transformers that have the highest GIC, and we put a blocking device in the model. And you see that the voltage collapse now moves out to a higher volts per kilometer, higher geoelectric field. So we've gone through various scenarios, and this is just one snapshot of this. So this is 5 transformers protected, 10 protected, 25 protected. And you see with 25 we moved out to 27 volts per kilometer. So we are improving the voltage collapse in the system by adding, in this case, 25 neutral grounding devices. We actually, the model, I should say, has 794 transformers in it. Covers 115 kV all the way up. So there's a lot of data in here, and we even took the case where we put neutral grounding in every transformer, and it moved the geoelectric field for collapse out to 75 volts per kilometer. There are still some ground connections in the model. Okay. So kind of the summary of those results. I think I'm missing a slide here, but when we compare to what is the 100-year storm, and I think that's the slide I'm missing. When we compare, we used John Kappelman's work, and we found very good correlation with Ante Pokeman, his recent results, if you consider a storm of 4,800 nanotesla per minute. And that value that Ante Pokeman came up with was 20 volts per kilometer for Quebec, and that's similar geology, similar soil to kind of the a lot of the northern states in the United States and in Canada. So 20 volts per kilometer. And he has a range that he projected, which was quite wide right now. It's 10 volts per kilometer to 50 volts per kilometer for regions like Quebec and the northern states. And what we're seeing here is collapse at 21 volts per kilometer. And we probably still have some errors in our modeling for the Wisconsin grid. So there's probably a range on there of, say, 15 to 25 volts per kilometer. But these ranges are just overlapping, and we're going to have to protect to the higher limit. I just summarized here that the putting 10 units in gave us an improvement of 26%, and then 25 gave us an improvement of 29%. We found that if you block, and our Wisconsin friends, ATC, are putting a plan together to put one of our units in their grid. So we did a run with one, and you see very little difference on voltage collapse, not much at all for one transformer. But of course, remember, if that's a transformer, an older transformer, you're going to extend the life of that transformer. It's not going to be, you're not going to be putting GIC through it, and so the transformer is going to last longer. Let's see here. We recently were asked by the military side for protecting bases if there was a possibility of a smaller unit, and so on the drawing boards we have a smaller unit shown here, which we're calling SG5. It's the SG22 that's already been tested, built, ready to go, and going in a grid. And in that regard, when we look at the generation, transmission, and distribution, that the smaller unit would be used over here on this side, the distribution side, whereas the bigger unit goes on the generation and transmission side. Okay, now I'm going to skip over to the inferential detector. It's an EMP RF detector, and this is the unit that we have tested, fully ready. We're getting ready to ship to one of our utility customers, and it measures up to 100,000 volts per meter with very fast rise time. It can measure the E1 pulse because it's got a less than 2 nanosecond rise time. Measures from 100 megahertz up to 10 gigahertz frequency range, and it measures either CW or pulsed measurements. So the idea here is to get the next slide up. Oh, miss it. Okay, there we go. So the idea is to place these, a number of these on a building and be recording activity. With a number of them, you can start to do directionality. You can couple these in with video cameras, security systems, and we already have the software display capability all up and running. This is kind of a indication of that. And then you can use this for alarms and recording. So then when you see something go past a certain preset level, you send out an alarm, and you're recording this information all the time. Let's see. That's it. Thank you for your attention.
I have one quick question as we get ready to transition. I understand I know you don't have time to get into this now, but I understand your firm's been doing some cost modeling, and the amount of money that you're anticipating the utilities to save in addition to other things would bring a return of an investment in what period of time?
Yes. Well, if you go into, if you get into a situation like Seabrook this last summer where they backed off generation and then had to go buy generation on a spot market, you find out that in a very conservatively low number, it's probably $24,000 per hour that you're spending when you have to suddenly go buy some power because you've been warned of a solar storm. And with this unit, we figure now that since it can be hooked up to several transformers in a substation, that the payback, if you're doing that kind of an operation, will be like 1 year. So it pays for itself within 1 year if you're going into uneconomic dispatch.
Thank you very much.
Okay.